Do you all see my main screen?
Yes, we do.
All right. Well, I'm very pleased to begin. And I thank the organizers so much for putting this workshop together. I know you had a really difficult time with the last moment Omicron virus news and other deliberations, but it's really a pleasure to be part of this adventure. So look, a theme for this workshop is soft robotics, materials and manufacturing processes. And I've been working on kind of soft robots for a long time, but one of the things that has struck me is that in many cases, I want robots that are soft in some ways, but then in certain ways, certain directions, certain attributes, they should be not soft. So I decided I would entitle this talk Selectively Soft Robotics. And let me explain a little bit what I mean by that. So here I am showing the octopus opening a jar. This is your classic example of a soft and powerful animal, and it's led to all kinds of interesting new manufacturing methods, for example, for making octopus robots. But as we think about it, even the octopus, which is our poster child for soft robotics, is not entirely soft. Cephalopods have a beak. The beak is composed mostly of chitin. It's interesting. It's a varying material property. It's 100 times stiffer at the tip at the base. And of course, if you want to tear and snip tissue, hard materials are a good way to do that. So we have been working for many years on bio-inspired robots. One of our collaborators on and off over the years has been Professor Bob Full across the bay at UC Berkeley. And when you ask Bob what are kind of some of the repeated learnings from biology for robot design, he mentions these points. And the two that I'm going to focus on are especially 3 and 4 today, this idea of using multifunctional materials and allowing those materials to help us interact with the environment. So a diagram that biologists like to show sometimes is this one. They refer to it as having a system where you have both active control, you have sensing, but you also have preflexes. Preflexes is the term in biology for passive mechanical behavior, like stabilization, for example, in the case of a cockroach. And the idea is that there are reflexes, there is lots of feedback going on, but this is wrapped around the inner passive behavior. And nature takes advantage of both of those. The other thing we find is that in biology, control and passive behavior are not separated. They're very much joined together. Now, of course, this makes analysis more complicated, but it also provides some advantages, and I'll allude to that a little bit later in the talk. Okay, so when we started out doing bio-inspired and soft robots, we used a manufacturing process called shape deposition manufacturing. And I feel a little bit like the old guy who says, oh, you know, back in my day when we did soft robots, we didn't have any 3D printers and we had to carve our soft robots out of stone. Well, maybe not quite that bad, but we did use CNC machines and we made molds out of wax, and we used those to cast polymers of different grades, hard and soft, in order to put together our parts. So let me give a quick example. This is an old one, but I still like it. On the left, we have an isolated cockroach leg. And this, by the way, is one of the advantages sometimes to working with insects like cockroaches, is that you can remove a leg and keep it hydrated, and you can actually actuate it and see what its force and motion properties are. On the right, we have one leg of a cockroach-inspired robot. And it doesn't look anything like the real cockroach leg, but it's a mechanism. And the pinkish material is a soft viscoelastic polymer, and the relatively clear plastic is a hard plastic, similar in properties to acrylic. And this is today, if I was going to make this leg again, I would probably do it by 3D printing with one of the new printers that can do both soft and hard material together. But we did it using that shape deposition manufacturing process that I talked about earlier. And so the point here is that even though it doesn't look like a cockroach leg, we were at some pains to replicate the behavior because we found that the viscous damping, and this is a hysteresis plot of force versus displacement for the cockroach leg. And you can see that as it goes through one cycle, there's a fair bit of energy dissipation, and it turns out that that's stabilizing. And so we were at pains to use again a viscous polymer that also had energy dissipation, and we were able to prove that it did in fact stabilize the robot and made it easier to control. So this is what I mean when I talk about using combinations of hard and soft materials and tuning them to get a behavior that you want. Okay, so now I'm going to go to my first main example. And this is the kind of moral to this story is about how do you integrate very hard, sharp materials with soft robots? Because that's a challenge. And the challenge we were given in this case was to allow NASA's RoboSimian robot, which you see kind of photoshopped onto a rock face here by JPL. This is a large robot. It's about 100 kilograms. And we wanted it to be able to climb rocky surfaces. So just ask yourself for a moment, what is a good technology for doing that? Well, what we came up with is that we would use multiple technologies. Some borrowed from human rock climbers and some from nature. We had learned years ago that spines are a good way to get traction on hard rocky materials. So our idea was to have a robot with a combination of feet and spines. And the implementation in the end turned out to be like this, that we had what we call soft and spiny paws in addition to feet that could support it from below. And then the spines can help pull the upper part into the surface and keep the robot from falling backwards. So the challenge here also is that this is a heavy robot. We had used spines before on other robots, but never on something this large. And so when you go into nature and you say, well, what kind of scaling would be appropriate for a robot of this size? And we're really talking about bear size, not insect size. But there's something going on here, which is that bear claws, well, they're strong. They rely on penetrating into the bark of trees, for example, in order to climb a surface. They won't work on something like a concrete building. In fact, when you look at spines and how they interact with surfaces, it turns out that the dimensions of the spine, especially the spine tip, are really dictated by the roughness of the surface that you want to interact with. So the bear claw scale doesn't really work. What we actually need are sharp, almost insect-like spines, but now scaled up to support a very large robot. So we have worked on various climbing robots over the years. The Rise robot that we did with Boston Dynamics, SpinyBot, and Scamp. But all of these are relatively small. They're all between less than a kilogram up to, I think the Rise robot was a few kilograms. So, but they all use spines about the same size. And what you're looking at here is an actual trace of concrete with a spine. And the spine has a certain tip radius. And what you can see is that as the spine interacts with the surface, what we get is what's called mathematically a traced surface, which slightly simplifies the profile. And if you think about the coefficient of friction and the direction that you would be applying a loading force, what you see is that it's these areas in green that I've highlighted here. These are the areas on which the spine would be able to afford some purchase and help you to climb a wall. And the green regions get bigger or smaller depending on how sharp your spines are and depending upon the approach vector that you come in with. And so this is something that you can calculate. We also learned that if you want to get the highest force density the maximum force per unit area of spines, the technology that seems to work the best is to have what we call linear spine arrays. And this is a matrix of spines in a 3D printed kind of array with, and they slide, and then you have either springs or you could use pneumatic pressure to push them in and out through the holes. And this technology is gives a little bit less load sharing than some of our earlier spine solutions, but it more than makes up for it in terms of density of force. And once again, depending upon, you can do some modeling of the spine surface interaction, and depending upon the angle that you have these spines at, and depending upon the roughness of the surface and the loads, you can compute what the maximum forces will be. So what happens when you actually scale this up is you can come up with a sort of expected value for the forces that you're going to get from a spine array. I should acknowledge, though, that it is stochastic. Spines, we don't know what the surface will be. As the spine comes and it approaches and makes contact with the surface, it might contact a very small bump or pit. We call that an asperity, as shown in the middle here, or it might come into contact with something larger. But that's okay. You can build a probabilistic model of spine surface interaction and come up with a probabilistic estimate of the maximum force that you could exert. And you can scale it up. So one of the problems is that if you just try to make these arrays larger and larger, it doesn't work. And the reason why is that what's inevitably going to happen is that a few of the spines will make contact early on and take most of the load, and then some of the other spines won't be very much loaded. And if you just load harder and harder, eventually what will happen is that those few spines that made contact first, they'll fail. They'll either deform plastically, or they'll cause the rock locally to fail and they'll slip off. So what we need to do is something called load sharing. And I'll come back to this again in another example, but the basic idea is here. So here we have an array of 4 by 3 tiles of spines. And what we've learned empirically is that the size of this tile is about as large as you can get before the load sharing becomes a problem. So the tiles themselves now need to share the load over the whole area of this large foot. And what we're doing here is we've got a tendon, and the tendon runs over pulleys, and the tendon is attached to each one of these tiles. So ignoring friction in the pulleys, if the tension in the tendon is everywhere the same, then the force on every one of these tiles also has to be the same. And we guarantee that the overall load for the whole matrix of 12 tiles is distributed evenly among each of the tiles. And so this is starting to get into this idea that I wanted to make the point of this morning's talk, which is that we're doing some kind of fun mixture of soft and not so soft robots. When you think about it, these spines are not soft at all. They're hardened tool steel, like a drill bit. And they need to be, because if they weren't, they would immediately become dull when you put them up against a rock surface. But we also need these kind of compliant load sharing mechanisms that one tends to see more in soft robotics. So I'm going to go to the last part of this slide thing, which is that what we wanted to do now is move to something that would climb irregular rocky surfaces. The problem with this tile solution is that it's good for climbing a wall, a flat wall, like a concrete wall of a building or a brick wall, but it's not good for a cliff face, because it doesn't have the ability to wrap around and curve over convex features. So what we'd like to do now is to take these spine concepts and put them on something that's more like a hand, or at least like a bear paw. Well, it doesn't work to just put spines on a hand. But there are some ways to get around that problem. And the questions that motivated this part of the work were, first of all, how can we actually combine spine arrays with compliant hands that can grasp rough and curved rock surfaces? And also, how can we integrate hard, sharp spines with a soft robotic hand? If you think about it, like that octopus with its beak, how do you integrate very hard materials with what is otherwise a soft robotic structure? The solution in the case of the octopus is that the beak is not of uniform hardness. It's very hard at the tip, and it's 100 times less hard when it is actually attached to the muscle that actuates the beak. So we need to do something kind of like that. And here is our result. So what you're looking at is one of the spiny bear paws that we built for RoboSimian. It has two main parts. It has fingers. The fingers are part of an underactuated hand, and they have those same kind of tile arrays that I was showing earlier. So many spines in little holes that can slide in and out and provide a fairly hard load. And then it also has a palm to help it grab surfaces. The palm is using a particle jamming approach. So that's also been a common thing in soft robotics, to have particles in a membrane, and you apply a vacuum, and when you apply the vacuum, it locks up. So it's very soft, very fluid when it's not actuated, and it can conform to surfaces, and you apply a vacuum and it locks up. So, I mean, that idea has been around, it works well, but the question is, how do we combine that with spines? How do we keep our extremely hard, extremely sharp spines from just tearing this sort of soft robotic particle jamming structure and causing leaks and maybe just tearing it apart? Well, it turns out that once again, you can take some lessons from nature. This is from a paper by Alexis Noel and David Hu, The Tongue as a Gripper. And many people are familiar with the cat's tongue, which is doesn't feel slobbery, you know, it's kind of dry and sandpaper feeling. If you go up to larger cats like lions and tigers, they actually have very large, very sharp spines on their tongues. But the winner in the spiny tongue category is the penguin, which has these amazing looking spiny tongues for ripping meat off the bones and so on. And what we discover in nature is that although these spines are hard and sharp compared to the tongue that they're embedded in, they've got a solution involving a kind of an intermediate structure of medium stiffness that anchors the spines on the tongue so that you don't have problems with stress concentrations. So pulling back a bit, the idea is that most soft animals or soft structures in animals, like, for example, the tongue or the octopus, they do have some comparatively stiff or perhaps at least inextensible elements. And they do that because, importantly, it increases their performance for certain tasks. So you do it because you need to do it. And doing so introduces some complications, like local stress concentrations, which you need to find solutions to. And it may also introduce new fabrication challenges, which you also need to find solutions to. Okay, so I'm going to play here a short video from this. I hope it works well on Zoom. And it illustrates kind of how this soft and spiny hand was put together. So there you see the spines coming out on the palms. Okay, one thing, I want to stop the video for just a second. One of the things that kind of surprises people about this, those spines are just wicked sharp. But there's no danger of them putting holes in this thin rubber glove. In fact, when you put your finger, if you press on the spines, it doesn't even feel uncomfortable because they're very softly sprung. What you cannot do, though, is pull tangentially, because if you do, then they'll immediately dig in and tear something. All right. Let me talk in a little more detail about how some of what you saw in the video, how it works. So in the palm, in order to integrate these very hard, sharp spines with a soft particle jamming palm, we needed to do something like what animals have done with their spiny tongues. We actually anchor the spines onto a small plastic platform of intermediate stiffness, and then those small pieces of plastic are supported by an elastic suspension system within the palm. And this has one kind of interesting advantage in this whole setup, is that if the spines engage with a relatively small little bump or a grain of something on the surface of a rock, we call that a weak asperity contact, then it's mostly the tip of the spine that will be making contact. It will have a fairly large lever arm down, with respect to the contact down to the base of the spine where this little platform is. And therefore, it'll be able to rotate the spine somewhat until the spine rotates and slips off and so on. And then the load will be taken by other spines. Conversely, if we have a strong asperity contact, we can have a larger force, but we also have a smaller lever arm. So it fortunately doesn't tend to rotate the spine around right away and slip off, which is a sort of a nice side effect. We also did, it turned out to be important to do some load sharing among the fingers. This is an under-actuated hand, and we have an array of spines at the distal phalange and at the proximal phalange. And now we need to share the load between the distal and the proximal phalange, and then also between the fingers. We're using a single motor in an under-actuated hand to activate this whole gripper. So we use fairly standard load sharing mechanism for under-actuated hands. It's called a whiffle tree. The motor is connected to this, what you see schematically shown in blue here, set of bars, such that the total force from the motor is distributed evenly among 6 tendons. And what we've done is we've run a separate tendon to the proximal phalange and to the distal phalange. So the distal phalange, out at the tip of the finger, there's a tendon that goes through the proximal phalange, but is free sliding. And then it's anchored in the distal phalange. And then we have a second tendon, which is anchored to the proximal phalange. And we approximate our soft flexure joints with a combination of linear and torsional stiffness. And what we would like is that when we load this thing up with the motor, we would like to get a fairly even force on all of these different components. And so we did, and the theory shows that for moderate curvature, you ought to be able to get that. And so we did some experiments to see how well that worked. And it actually worked quite well. The dotted lines in this plot are our theory for how the forces would evolve as a function of whether we were loading just the distal or just the proximal or both phalanges. And then the dots are actually the average of 4 trials of the experiment. And you can see the match is actually quite good. And that provides a nice way of integrating very sharp, very hard spines into a soft finger, a soft hand, and doing load sharing so that you get a fairly even force distribution over the whole area. All right, let me pause for a moment and take any questions on soft and spiny hands before moving on to my second example. You can put them in chat, or you can just ask them.
Can you hear us?
I do hear you now, yeah. Are there any questions?
I think I'll start with
Did we consider a hydraulic system? Actually, that's a good point. Another good way of doing load sharing is to have a hydraulic system. Yes, and we did. The robot, I mean, it's in fact a good approach. And the reason for not doing it was mainly just a practical one. RoboSimian is an electric robot. It doesn't have any hydraulics. However, it does have pneumatics built in. So it was easy to plumb pneumatics to the spines, low pressure pneumatics to force the spines out on the rocky surface. But we didn't, but to go to hydraulics would have required, then having a motor and valving and a hydraulic system. So as I said, it would have been a good solution, but it just turned out that practical matters of plumbing and so on caused us to use tendons and a whiffle tree instead. What happens when a similar spine is encountered? I'm not quite sure what that means. What's being asked there? Yeah. Okay. Regarding the next question, works well in terms of stability. Is it good also for driving the robot? Yeah, in fact, we were easily able to exceed the required weight. The robot, as I mentioned, is about 100 kilograms. It turns out that you could hang the whole robot from the weight of one hand. The spines themselves don't drive the robot up. The spines, what they need to do on the hands, they need to give a grip. And then there are actuators in the arms of the robot that cause it to take steps one after the other, attaching and detaching the spiny hands as you go. So the spines were not really intended by themselves to be a propulsion mechanism. Are the spines in the natural models distributed evenly? No, I bet not. And in fact, almost always when you look at nature, things are not uniform. They're spatially varying. And I don't think an even distribution works better. And I think if you were to do a formal optimization, you would discover that it might turn out that the spines, let's say at the periphery of a square array, should be longer than the ones at the center, because in order to ensure that you always get a good grip. How do we compare spine mechanism with suction? Well, suction, unfortunately, doesn't really work well on rough, rocky surfaces. It's hard to get, I mean, these are really rough. So unlike brick or concrete, it's actually hard to get suction to work well, even if you're not trying to make a seal. If you're just trying to, pull yourself into the wall with a Venturi effect or something like that, it's actually very hard to get the kind of forces you would want. So I think in this application, suction was not a reasonable approach. It might be on a more flat, more uniform wall like brick or concrete. Are the natural spines on, what about combining macroscopic? Okay, there's a couple questions here. Let me take them one by one. What about resistance to lateral forces? Well, that's actually the spine's resistance to lateral forces. I'll get into this more a little later. It turns out that the spines, if you angle them a bit, they'll have the best resistance if you're pulling them against the direction that they've been tilted a little bit. But they also have some resistance laterally. And what you get is a kind of a bowl-shaped surface in force torque space, which is longer in one direction and a little shorter in the other direction. The lateral resistance of spines to shear forces is pretty good, actually. Let's see. For this design, could it be applied to hang? Yes, it could. What you need to do then, and we've done this for things like perching quadrotors that perch on a rough ceiling. What you need to do is to have two sets of spines. Let me stop sharing for a minute so I can show this. what you need to have then is two sets of spines that pull against each other. And so it will turn out that the major force is in the horizontal direction, but you also can do some vertical. So when we have grasping on the ceiling, like a rough ceiling, like I don't know whether the ceiling in the lecture room where you're all sitting is rough enough, but anyway, we could try it with a quadrotor. We do this sort of opposed spine gripping. Let's see. Are the natural spines on the tongue not made of soft tissue? They are not soft. They are made out of a hard material, sometimes chitin, sometimes dentin, like teeth. Just the same way that pincers or on the claws of a crab or a lobster or the spines of an insect, they're hard the same way, or even teeth-like in terms of a pendant. So they get their stiffness, their rigidity from the material properties, and that's why it's sort of interesting to see how they integrate that with the soft material that they're attached to. What about combining macroscopic spines with nanospines? Yes, gecko materials. Well, I'm going to talk about gecko in the next few minutes. We have thought many times about combining spines with gecko adhesion. The trick is that you need to do something to protect the gecko adhesive when you're on very rough, abrasive, rocky surfaces, because it will damage, it will abrade the gecko materials. And finally, what's the maximum angle of inclination? I don't remember what it was in the case of RoboSimian. The problem is RoboSimian was not designed to be a climbing robot. So its center of mass is actually some ways out from the wall, and that really is fundamentally going to limit it. Let's say maybe 80 degrees or so. If you make a very flat robot like SpinyBot or the Rise robot we did with Boston Dynamics, that will do an absolutely vertical wall. And as I said, if you want to do something like a perching quadrotor, if you're willing to go to having opposed pairs of spines with inward force, then you can even perch on a ceiling. And finally, are spines able to grasp glossy and smooth surfaces like glass? No, absolutely not. For that, we have another technology, which I think I will go to next. Unless there's one more question, which I could take before moving on. Yeah.
Is there also an application in grippers, like for construction or so? So that
it's something that we've talked about. For construction materials and so on, I think you might be able to do well. When we've talked to people about gripping other things, as soon as they say we're going to contact their product with a whole bunch of very sharp spines, they get less enthusiastic about it, and they would rather talk about gripping with gecko adhesives, which we've actually done more work on. We've made a bunch of grippers that use gecko adhesives. Spines actually work well, as if you're careful with them, they're actually fairly gentle, but they've been less popular for gripping. All right, thanks. Those are great questions. And if I missed you, please bring it up again at the end, and we can come back. But I'm going to go ahead and talk about example number 2 now. So I'm going to share my screen again, make sure I'm optimized, and take over. All right, geckos. So yeah, probably the best known technology out of my lab is the StickyBot gecko-inspired robot. Gecko adhesion is a very interesting.
One second. Can you chat screen, because it's.
I'm sorry, what?
Can you move your the chat screen from your screen?
It's sharing that as well. Okay, yeah.
Yeah,
So yeah. I may need to stop sharing and reshare in order to do that.
Yeah, it's better. It's still there at the top, but I don't think we can do anything.
I don't know if I can get rid of that. I think that, unfortunately, that's my Zoom. Oh, I see. You want to, okay, I can maybe do one more thing. I don't know if I can completely get rid of it. I can minimize it.
Yeah, I don't know either. If anyone in the chat knows, we can suggest. But
Yeah,
otherwise, it's still fine. It's just in the top corner.
yeah, I can push it way off to the side as much as much as possible.
That looks fine. Thanks.
All right. Yeah, so Gecko Adhesives. We worked at some length with biologists, Keller Autumn and Bob Full. One of the amazing things about Gecko Adhesives is this multiple length scales that you have to think about, where it conforms at the centimeter scale, at the hundreds of micrometers, at micrometers, and you go down to these tiny spatula tips, which are just 200 nanometers across, which of course represents a really challenging fabrication problem. So what are the principles for climbing with Gecko adhesion? Well, we knew early on, just looking at that previous slide, we knew that compliance was going to be important. So we need to conform to surfaces at multiple length scales. You need to do that to get a large area of contact so that van der Waals forces will let you stick. So we built a very underactuated system that allows a sticky bot to do that. One of the things that we didn't maybe realize quite as much early on is how important the directional nature of adhesives is. So the ones that we use now are microscopic wedges, about 40 micrometers wide at the base and 80 to 100 tall. They taper to very sharp tips around 1 or 2 micron tip radius. And the point is that when you bring them in contact with the surface, initially it's just the tips that are making contact. And so the area is very small and they're not sticky. But when you apply a tangential force, a load force as shown here, they bend over and now you have a large area of contact and you get the van der Waals adhesion that is what makes them stick. And finally, given the fact that we need to control compliance and tangential load, this also has implications for doing distributed force control, which I won't talk about as much today. All right, so I'm going to pause my sharing for a moment so that I can show you something. If I were there, and I wish I were there, I would pass this around. I have here a ball with a little bit of the Gecko adhesive on it. And I can use the adhesive to support the ball. And, you know, that's fine. That's not so exciting. I mean, if I had Scotch tape or some sticky tape, that would work too. The difference is that if I had sticky tape, it would stay stuck, whereas this is not sticky. It comes right off. And if I were passing this around for you, you would be discovering that, first of all, if you touch it, it's not sticky at all. It just has a sort of rubbery surface. And the second thing is that no matter how closely you look, you cannot see the features. They're truly microscopic. And I can hold them way up, but there's no way you're going to see these features without a microscope. Okay, so let's go back and talk a little bit about how it works now. So what I just showed, this is a stylized version of what I just showed you. There's the ball, I've got 2 pieces of tape and I'm pulling on a string in the middle. And in so doing, I'm applying that tangential load onto the wedges that causes them to bend. The wedges look like that if you were to zoom in with a microscope with their sharp little tips. Okay, well, but there's a little more to it than this. Actually, the way I'm using this tape on the ball is not very efficient. First of all, the part of the tape that's up here that's not making contact with the ball isn't doing any good at all. And then the part that is making contact with the ball has this kind of linearly decreasing tension in the film because you're integrating essentially the shear stress as you go. But it's even worse than that. If we look at it in even more detail, and this is a simple model, I didn't put equations in, but I think you can get the idea from this. So here I have my surface of the ball, which at the scale of the wedges is not perfectly smooth and flat. It's going to have a little bit of waviness to it. And that's why I like to put the wedges on a thin film. It helps them to conform to a surface. And now the wedges themselves, each wedge is represented by one of these little springs, K sub S, and it has a certain stiffness and it can bend and it can stretch. And the film that I've been put all these wedges on also has some stiffness per unit length. I'm calling that KP. And if I apply now my load force to one end, T, tension in the film, there will be a certain motion that each, if I discretize these into elements, there will be a certain amount of motion, delta sub n, at each location along the film. And without putting all the equations down, it's easy to convince yourself that even if the film is relatively stiff compared to the wedges, even if Kp is much greater than Ks, unavoidably, I'm going to have a non-uniform shear stress because this piece out at the edge here will stretch a little bit and this piece of adhesive will stretch a little more, whereas by the time I go all the way down and propagate to the far left, there's going to be not as much relative motion. What we would like ideally, what we would like is for every single wedge to have exactly the same force. And if you could just think about that for a minute, how could I get that? How could I make it so that every little gecko wedge has the same force as all of its neighbors, even though they're on some large surface with a piece of film or whatever, and I'm applying a load from one end? And it turns out that this is important because this is necessary if we want to scale gecko adhesion to large loads. Shortly after we did this paper with Elliot Hawks climbing a building using our gecko adhesives, a group at, actually, I think it was Cambridge University in the UK, came out with a paper proving that the gecko was the largest animal that would be able to use gecko adhesion in order to climb. And the largest geckos are less than 1 kilogram. Well, Elliot obviously weighs more than 1 kilogram. So what's going on? What's going on is we need to do a much better job of load sharing. And the problem here is this. As you get larger, of course, your weight grows as length cubed. It grows as your volume. Therefore, as you get larger, ideally, the available adhesive pressure that you're getting from your gecko adhesives should increase with size. Unfortunately, what we and everybody else who works on gecko adhesives has found is that as you go to larger areas with your gecko samples, the available pressure doesn't increase, it decreases. It decreases significantly because there are imperfections in this load sharing. And it's captured rather nicely in this log-log plot. The top in red is from the gecko. And by the way, the gecko also doesn't do a perfect job of load sharing. In fact, not at all perfect. So if you do tests on individual gecko setae, you get rather high shear stresses, adhesive shear stresses available. And if you go to a group of setae or a whole toe, one toe, or finally the whole foot, it just drops. And it's approximately linear on this log-log scale. And you can see that indeed it's true. If I just extend that line, I am not going to make my goal, which is here shown in green is the approximate range for human climbing. If you take the available area and the weight of a human being. If I just extend that line, I'm going to miss my goal. Meanwhile, down here in blue is our synthetic adhesive system. Well, it's even worse. You can see at the same length scale, we're actually well below. Again, remember, this is a log-log plot. We're well below where the gecko is. And if it goes at the same rate, we're not even close. We're no way are we going to be able to support human scale climbing. So we need to do something much better. And the problem is that just being soft isn't good enough. And this is a nice diagram from Bharat Bhushan and his lab. You can think of it as your compliance as being a hierarchical system of springs. But you can see what the problem is here. If I take these springs and I push them against a rough surface, what's going to happen is that some of these springs here are going to make contact first, and then the ones that have to go all the way down into a valley are going to make contact later. Okay. So now what happens when I pull? What happens when I pull, of course, is that the ones in the valley are going to detach first because they're going to reach their limiting stress before the ones on the peak of the hill. And when they detach, unfortunately, what happens is you get like a crack that propagates, and then the whole thing, it's like an avalanche. The whole thing fails in propagation. So the problem is local stress concentrations and stored potential energy, it propagates and you get a failure. And this is what fundamentally causes relatively poor adhesive scaling performance. Well, when I think about what the ideal solution would be, I'm reminded of the famous story by Tom Swift, Gulliver's Travels, where he's held down to the ground by the Lilliputians, and they're using tiny silken threads. And each thread, of course, is very weak, but they've got so many of them and they've tensioned them all just right so that, in fact, he's completely immobilized. Ideally, this is what we would like to do. So what are the ways? Well, one way is to do like we did on the palm with the spines. You have either a phase change material or a jamming material. So it's soft, you press it against your irregular surface, you let the gecko materials all conform. So in that sense, you know, it's like this spring thing. It's soft initially, we come down, but then once we've made contact with the surface, we lock it up and we become rigid. So I could use, for example, a low melting temperature alloy or something that would lock up. Or I could use a mechanical or hydraulic differential. And somebody mentioned with the spines earlier, what about instead of using a whiffletree, what if you used a hydraulic system for load sharing? And yes, that's equivalent. That would do a good job. Or you could use an array of degressive springs. And this is the one that we in the end actually used for climbing. And I'll explain how they work in a moment. These are springs that are non-linear. And so when you first load them up, they have all different forces, but then they all plateau at the same level. And so once again, you get good load sharing in the limit. And in fact, yeah, here's exactly that point. So on the left is a differential. It could be a whiffletree, it could be a hydraulic system, it could be a tendon pulley system. But the point is that it's a well-known solution where you have a load that you need to pull. In this case, it goes back to even Roman times where you have draft animals like oxen, 1, 2, 3, 4, 5, 6. And if one of them gets a little bit ahead or behind its neighbors, that's fine. These things pivot and the total force is still the same. So that's a differential. Degressive springs are what's shown on the right. And there are some that have that property. If you use shape memory, if you use a nitinol shape memory alloy, they have a kind of linear stiffness, but then they plateau. And the way that works is that you share the load, even though they may start out differently. If they all plateau at the same maximum force, then in the limit, you're going to get good load sharing. So that's in fact the system we used with a system of tiles. And you can see here our blue, this is where I was showing you the Gecko adhesives before. A single tile gets a fairly uniform force over the tile. And finally, we used an array of degressive springs, and that's what allowed us to meet our goal. So that provides a nice way of scaling. And what that led us to do next, and this is the last example I want to show, is a project with NASA to grab large objects in space. So seeing that result, NASA contacted us about whether Gecko adhesives might be a suitable technology for grabbing space junk. And once again, because these objects are large, we're going to need to do some load sharing. The good news is that we're in zero gravity, so the forces are not as large as they would be if you were in a gravitational field of Earth. But it's important to go up and just contact them very gently and latch on without accidentally forcing them into a new orbit. So there's an early prototype grabbing a solar panel and lifting it. Okay, so I'm going to show a short video here that explains the technology, and then I'll have a few final slides that describe how it works in more detail.
The amount of space debris has been growing exponentially in the past several decades. Space debris can possibly crash into new satellites and cause catastrophe. One way to prevent this from happening is to grasp and recycle the debris before a tragedy happens, like in the movie Gravity. At Stanford JPL, We have learned from gecko lizards to make small adhesive grippers that adhere to smooth surfaces such as solar panels and fuel tanks with really little attachment and detachment effort. This is a nice solution for grappling and releasing free-floating objects. We then efficiently scaled the gripper up and added a special wrist design to enable the grasping and manipulation of large objects. Experiments have been conducted in the NASA JPL air-bearing floor, also known as the Robodome, where a 400 kg master robot with the gripper tried to grapple another 400 kg slave robot by grasping a solar panel. Either controlled by a human or autonomous thrusters, the master robot successfully grappled the slave robot with only a slight push but large adhesion. The wrist acts like a non-linear cushion that absorbs energy during impact but stays stiff during manipulation. Misaligned grasping is also demonstrated here. For a full 3D floating test, we built an even larger gripper that can grasp both flat and curved surfaces with a larger safety factor. Experiments were conducted in the NASA zero-gravity airplane, also known as the Vomit Comet. In the flat gripper mode, the gripper grasped a cubic object much larger than itself with little pressing force. When detaching, the gripper does not affect.
Okay, I'm going to stop it for just a moment because I want you to focus on what happens when he lets go.
The object's motion state. This is very different from conventional sticky materials.
Nothing. And that's essential.
Similar functions have been achieved with the curved gripper. Little attachment force, strong grip, and clean detachment. Spherical surface grasping has also been conceptually proved with a beach ball. Although it does not require much adhesion, it does require a very tiny engagement force because it is easy to knock the ball away. Earlier this.
All right. So how did that work? In this case, because we wanted to do even load sharing, not only at maximum force, but at all levels of force, we went back to using the differential idea. What you saw on the video at one point was an array of little flat tiles. And what we do is we take opposed pairs of tiles. And this is the same idea as what somebody asked earlier about the spines. Can you grab the ceiling? Whether it's with spines or with gecko adhesives, the way you get a pure normal force is that you have a tendon on a pair of them equal and opposite, so that they're pulling against each other, and then you can get a net force in the perpendicular direction. So we have pairs of tiles, and each pair of tiles is then connected to this tendon system where, again, ignoring friction, you assume that you have the same tension everywhere along the tendon, and therefore every pair of tiles should have the same force. And this is what allows us to scale adhesion up to large areas and large loads without running into that issue that we saw with the gecko where it drops. It seems like a totally new idea, but I'm in Italy right now. And of course, anything that you invent, somebody will tell you that Leonardo da Vinci already invented it. Well, not quite this. But he does have this nice example in the notebook where he points out that you could use a whole big block and tackle system with many pulleys such that you could weigh a weight of 1 pound could lift the equivalent of 33 times more through mechanical advantage. Although interestingly, what is being said in this museum article also is that he was ignoring the effect of friction, which is in fact noticeable. And we've noticed that too. We're using ball bearing pulleys, but we're kind of limited. We were at the upper limit, I would say, for how many pulleys you could have and still reasonably assume that the tension's fairly uniform. And you would probably have to go to some hierarchical system if you wanted to make it even bigger. So what are the merits? Well, as I mentioned, the digressive system, which is what you see on the right, the way that works is that as different tiles make contact, some sooner, some later, they go up at different rates, but then when they plateau, they all kind of converge to the same force. And that worked for human climbing, and we used it because it was very lightweight and relatively simple. The tendon system, in contrast, gives you a nearly uniform load sharing across all different levels of force. So it's more complicated, but it does have that advantage. And which one is preferable? Well, that's where other practical issues come in: complexity, robustness to failures, scaling, friction, and so on. All right, that ends. And at this point, I'll open it up and take questions. And I thank you for the questions we had earlier, and I look forward to some more good ones. And I'll open up my chat window again.
Thank you, Mark, for that.
Well, there was one early one there. Do gecko grippers lose adhesion in dusty environments? Yes, they do. Not as fast as conventional adhesive tape, but they will eventually. Now, it helps that they're not sticky, and therefore they tend not to attract dust in the first place. Actually, if these do eventually get sticky, the best way to clean them is to take a piece of standard adhesive tape and press it against the surface, and it pulls all the dust off. You know what? It's like, you've seen those lint rollers that you can put on your suit to take like cat hair off your jacket or something? That works also really well for cleaning these. But eventually they do become sticky and in a dusty environment, and eventually they would need to be cleaned. In contrast, the gecko is even less sticky than this. So much less sticky that on almost any surface it contacts, the dust is preferentially attracted to the other surface and not to the gecko. There are exceptions. White dry erase boards, the kind that you mark on with markers, geckos do not self-clean on those surfaces. And you can maybe imagine how that was discovered in Bob Full's office at Berkeley. Other questions?
Thanks, Mark. It's very interesting. I'm curious about the design when you mentioned that you have to make sure they have the force the same direction in the gecko wedges, for example. So in case of failure, I make sure that's have kind of redundancy to the mechanism to catch the object. So in case of failure, mainly, if there's failure, is a design. One part of the wedge, I will make sure it's redundant.
Right. So there's a couple, if I understood your question, there's a couple parts to that answer. The first is that the gecko wedges, although they grip more strongly when you pull in their preferred direction, they actually grip about 2/3 as strongly if you pull them with a lateral or tangential component. So you don't have to have the orientation absolutely perfect. If you really want to grip in all directions, then you can make an array where wedges are oriented in different directions on different parts of the surface so that some are optimized and some not. Now, what happens with failure? How do you make it robust to, yes, because what will happen is that probably in a regular surface, some of those tiles may not make good contact and they may come off. And so it's important with load sharing that doesn't propagate. And so what you need to do is you have to have some limit stops. So although the tendon going through all the tiles is supposed to give them all the same force, we've also put limit stops in so that some tiles pop off. Well, they just pop off, and then you have n-1 or n-2 tiles taking the load. Okay, let's see. There's another question in the chat window. Do you think advances in this field rely more on materials, manufacturing processes, or both? Yeah, both important. In fact, after many years, I think we're finally on the cusp of having a good manufacturing process for the gecko wedges. There's a former student who's got a startup company in California who's now starting to be in the business of producing them. Up until now, making little samples of gecko wedges, it was almost like a craftsman process. We would carefully train graduate students, and they would spend hours making these molds by micro machining, and then we would get the wedges. So manufacturing is absolutely important. If you want an analogy, you should look at Velcro. When Velcro first came out, it was a sort of weird and special technology, and people only used it in very special applications where almost nothing else would work. Now, of course, there's many types of Velcro. It's very cheap. It's used everything from shoes to the seams of hot air balloons to medical devices. And that kind of shows the power of manufacturing when stuff really becomes available. There are also things that can be done for materials. We've been using a silicone rubber. It's a room temperature cast silicone rubber, just like a lot of you guys use for doing soft robots. It's okay, but it's not super strong. If you go to a store to buy a spatula for cooking, a silicone rubber spatula for cooking, that is a different kind of silicone rubber that is only manufacturable by hot compression molding. It's much tougher. You can put it in the freezer, you can put it in boiling water, and it's fine. So one of the things that we're actually looking at with manufacturing processes for the Gecko materials is to be able to go to hot compression molding, which would let us use much tougher grades of the elastomer that would be longer lasting.
Hi, Mark. Thanks for your talk. I would also have a question. You showed the grippers who work really well in space, but like the objects were more or less not moving, but you mentioned the example of removing trash surrounding the Earth, and there the objects are moving really with high velocity. Do you have an idea how to grab them when they move with high speed?
That's a controls problem. So you need, I mean, you cannot, if you just try to reach up and grab something that's moving and spinning really fast, you're not going to catch it. The inertial forces are going to be really high. And even if you did catch it, you now suddenly are a combined mass with this thing going off. No, you need to use your rocket to accelerate yourself and match whatever the trash is that you're trying to grab so that there's less than a meter per second of velocity difference between you.
Hello, Mark. Thank you for the talk. How does the temperature variation comes into play? And what if the surfaces are, what if the surfaces are wet or with, how does that affect?
Yeah. Okay, so temperature variation, it turns out, is not too bad. Actually, but fortunately, it turns out that there are space qualified versions of this silicone rubber that one can use. And actually, we just had some Gecko grippers that went up into the International Space Station. And they did some experiments last spring with them. Silicone rubbers, as elastomeric materials go, are actually quite tolerant of high and low temperatures, which is why, in fact, silicone rubber cooking spatulas are good. You can put them in your freezer and they're fine. You can put them in boiling water and they're fine. You can actually go down to something like -60 degrees centigrade and they're fine. And you can go up to a couple hundred degrees centigrade and they're fine. Beyond that, you would need to do something. You would need to use maybe a Peltier junction or something like that to keep the temperature within that fairly generous range. Now, what about moisture? Moisture is a problem. Even for geckos, it greatly reduces their adhesion. And the problem is that water is a polar molecule. So it actually reduces the van der Waals force. Now, geckos, they do work in jungles where it's steamy and moist. But they also have about a safety factor of something like 100 to 1, where we don't. So even though they lose some adhesion, they still do fine. But our Gecko adhesives basically do not work at all on wet surfaces. What are some natural internal failures? Natural or internal failures of? Yeah, well, this is a similar question. Again, moisture, especially with a polar molecule like water, causes problems. There are other biological gripping techniques, for example, mussels or barnacles that have been studied that do work very well underwater. The problem is that they tend not to be appropriate for this sort of very fast, instant on, instant off kind of behavior. We need something that allows a small climbing robot to take hundreds of steps per minute. And so it needs to be a sort of, like what's going on here, it needs to be something where it's not sticky, but then the instant I try to apply a load, it immediately grabs and allows me to apply some force. But moisture is definitely one problem. Also, our Gecko adhesives do not work well on surfaces that get too rough. So something that's kind of smooth, a little bit glossy is okay. But on rougher surfaces, we don't grip. Interestingly, though, the Gecko does, because it has that hierarchical system that I showed at the beginning of the Gecko thing, you know, from centimeters down to nanometers. And so it can reach into the valleys more for rough surfaces. Any other questions? Rotation of objects seems, yes, rotation of the object is critical. Actually, we have papers on this with Marco Pavoni. He's a professor of aeroastroengineering at Stanford, a controls expert. And what we found with the rotation is that, and you can kind of guess what's going to happen. If this is a piece of space junk, it turns out that if it's rotating this way, and I do it, it actually helps. It kind of wraps it in and grabs really well. If it's rotating the wrong way, this way, then it kind of wants to peel off. So what you need to think about, either in designing your gripper or else in designing your control system where you approach the object, is to account for the direction of the spin so that it kind of wraps itself into your gripper and doesn't try to wrap itself out. Any other questions, either chat or in the room? By the way, these are great questions. It's a lively audience.